It's small, it's dark, and it has a colossal mass. Those three facts alone point to the existence of a supermassive black hole. It can be frightening to consider the perils that may be found in the great emptiness of space. This is true for the idea of space travel as a whole, but black holes are one aspect that has always fascinated and alarmed people at the same time. Numerous studies have been conducted on these powerful creatures all throughout the world. Researchers have been attempting to determine the nature of black holes and what is contained within them. But that all changes right now. Recently, Neil deGrasse Tyson made a stunning discovery. Our black hole is smaller than the one at the center of the Andromeda Galaxy, which is our closest large galaxy. I believe that humans are envious of black holes. It might just blow your mind to see what's inside a black hole now that we can finally see it. A black hole is formed when a large explosion concentrates its mass in a very tiny area, producing a gravitational force that is so strong that nothing can escape from it, not even light. Anything that gets inside will be there permanently. These energy sources range in size from stellar black holes, which have a mass a few times that of the Sun, to supermassive black holes, which are found at the centers of galaxies and have masses millions or even billions of times that of the Sun. For decades, scientists have been witnessing black hole phenomena indirectly. But with each new piece of information, additional mysteries are revealed. They do have an origin story, despite the fact that they appear to be so enormous and strong that it is unimaginable. Not only can black holes exist in space, but they are also formed. To be born, they require the remains of enormous stars that have run out of nuclear fuel. These stars explode as supernovae, a dramatic occurrence that signifies the end of their existence. A supernova causes the star's core to collapse due to gravity, while the outer layers are forcefully ejected into space. The force of gravity overcomes all other forces, forcing the core to collapse inward, if the mass of the core is several times greater than that of our Sun. A black hole is created when an object with a gravitational field so strong that nothing can escape its grasp collapses, compressing the material into an extraordinarily compact volume. A black hole's mass determines how big it is. The most well-known kind of black holes are stellar ones, which range in mass from a few times to several tens of times that of the Sun. The singularity, an area of infinite density and space-time curvature, is located in the center of a black hole. The laws of nature break down at this point, as far as we can tell from existing physics, and conventional theories are unable to adequately explain what occurs inside the singularity. A singularity in physics is a location in space-time where a certain quantity becomes infinite or undefined. Singularities arise theoretically in places such as black holes and the Big Bang singularity, the beginning of the expanding universe. A significant problem that emerges when studying the Big Bang singularity is that the laws of general relativity, which control the behavior of gravity, degenerate as one approaches this starting condition. To tackle this problem, a new theory fusing quantum mechanics and general relativity is required. Singularities are found near the center of black holes, where the gravitational attraction is infinitely strong. As matter and energy enter a black hole, they approach the singularity and undergo infinite compression. This idea beyond what we currently know about physics. A theory of quantum gravity, which attempts to combine general relativity and quantum mechanics and provide insights into singularities and the workings of the universe, has been pursued by scientists in response to the problem of singularities. Loop quantum gravity is one method of dealing with singularities. According to this theory, space-time is quantized, or made up of discrete, indivisible units at very small scales. These units are spin networks or connected loops. This theory holds that infinite densities and curvatures, which lead to singularities in classical general relativity, are prevented by the discrete character of space-time. Space-time shrinks as matter falls toward a black hole's core, keeping the stuff from attaining an eternally dense singularity. Rather, in the vicinity of the core, the compressing matter experiences a quantum bounce, after which it expands. As a result, an entirely new space-time region, sometimes called a quantum black hole, forms inside the black hole. The most frequently detected kind of black holes, stellar black holes, are created at the end of a large star's life by gravitational collapse. A star collapses under its own weight and forms a stellar black hole when its nuclear fuel runs exhausted and the outward push from nuclear reactions is no longer able to oppose gravity. Stellar black holes are exceptionally dense due to their small size, only a few kilometers in diameter, despite their mass. A stellar black hole's extreme density causes an event horizon to form, which is the limit beyond which nothing can escape. The point of no return, or the event horizon, is where information or an object crosses the force of gravity and becomes permanently trapped. With masses ranging from thousands to tens of thousands of times that of the Sun, intermediate mass black holes have an impact on their surrounds and the evolution of the galaxy. Supermassive black holes, which are frequently located in the centers of galaxies, are still being studied. According to one theory, they developed from smaller black holes through a process called accretion, in which matter gathered around a black hole eventually merged to become a supermassive object. Reissner-Nordstrom and Kerr black holes are examples of special cases of charged black holes. While Kerr black holes are both charged and revolving, bringing in unusual phenomena like frame dragging, Reissner-Nordstrom black holes are charged but non-rotating. Since the majority of black holes are neutral and do not have a net electric charge, these kinds are primarily theoretical. As technology has advanced, scientists have made direct observations of black holes. The first photograph of a supermassive black hole in the galaxy M87, which is 55 million light-years away from Earth, was taken in April 2019 by the Event Horizon Telescope. Additionally, significant advancements in the confirmation of black hole existence were made when gravitational wave observatories like LIGO and Virgo observed ripples resulting from black hole collisions. Black holes exist, even though our understanding of them is still incomplete. It is essential to keep researching them in order to comprehend the nature and behavior of the universe. Although the exact mass range of intermediate mass black holes is still being investigated, it is generally accepted that their masses vary from thousands to tens of thousands of times that of the Sun. These enormous objects are found in the centers of most galaxies, including the Milky Way. They have a strong gravitational pull that shapes their galactic environment and affects the evolution of galaxies. One of astrophysics' greatest mysteries, the creation of supermassive black holes, is still mostly unknown. Nonetheless, a number of explanations have been put up to account for their beginnings. According to a well-known theory, supermassive black holes form through a process known as accretion from smaller black holes. In this scenario, stuff, including gas, dust, and stars, gathers around a black hole to form an accretion disk, a spinning region. This material spirals into the black hole and eventually merges with it over very long times due to the black hole's strong gravitational attraction. This ongoing process of matter accretion enables the black hole to reach gigantic proportions. Massive amounts of gravitational potential energy are released as matter falls into the black hole during the accretion phase. Some of the universe's brightest and most potent phenomena, such as quasars and other active galactic nuclei, are propelled by this energy release. Charged black holes, an intriguing variant in black hole theory, are located apart from these supermassive black holes. An electric charge is a characteristic of charged black holes. Reissner-Nordstrom black holes and Kerr black holes are the two primary varieties of charged black holes, based on the interaction between the black hole's charge and other variables, including spin. Each form displays unique traits. The Reissner-Nordstrom solution in general relativity describes Reissner-Nordstrom black holes, which are charged but non-rotating. These black holes have an event horizon, whose size is dependent on both the black hole's mass and electric charge, even though architecturally they resemble uncharged black holes. The charge of these black holes influences their gravitational field. Conversely, Kerr black holes introduce special phenomena like frame dragging, where the rotating black hole twists the surrounding space-time, because they are both charged and rotating. These black holes have an inner region known as the Cauchy horizon, which is a border that divides the singularity within from the outside, in addition to an outer horizon. In addition to gravity, the existence of an electric charge in a black hole creates a repulsive electrostatic force that influences the behavior of surrounding particles and matter. For example, the electric charge of the black hole may resist charged particles, changing their trajectory. Though theoretically feasible, charged black holes are not commonly anticipated to form in the natural world. It is believed that the majority of black holes originate from astrophysical processes that produce neutral objects, or ones that have no net electric charge. In the event that a black hole were to pick up an electric charge, it would probably eventually balance itself by drawing opposite charges from the environment. Though much has been discovered over the years about black holes, witnessing one alters our understanding of these mysterious objects. Thanks to the quick advancement of technology, scientists can now see and verify the existence of black holes. In fact, two groundbreaking observations have shown direct proof of black holes. The Event Horizon Telescope team took a picture of the supermassive black hole at the heart of the galaxy M87, which is situated around 55 million light-years from Earth, in April 2019, marking the first direct sighting of the object. The picture displayed a luminous ring of. The event horizon of the black hole is represented by the hot gas around a dark center region. This discovery offered previously unheard-of visual proof of a black hole's event horizon and surrounding accretion disk, in addition to confirming the existence of supermassive black holes. Later, more observations were made by gravitational wave observatories such as Virgo and LIGO. They observed rippling effects in space-time resulting from black hole mergers and collisions. An enormous scientific advance was made in 2015 when gravitational waves were detected, establishing the existence of binary black hole systems. Systems in which two black holes orbit one another before merging and generating strong gravitational wave signals. For a very long time, black holes have fascinated scientists and the general public alike, giving rise to a plethora of ideas and conjectures on their nature and function in the cosmos. More than ever, researchers may now delve deeper into the study of black holes thanks to recent developments in observational technology. For instance, a new field of research in astrophysics has been made possible by the discovery of gravitational waves resulting from merging black holes. These waves cause ripples in space-time, which scientists may use to investigate these elusive objects. There are also fundamental problems concerning the structure of the universe itself that are related to the study of black holes. A prominent field of study is the possible relationship between dark matter and black holes. Dark matter, which accounts for a considerable fraction of the mass of the universe, is still mostly unknown. According to certain hypotheses, some of the enigmatic dark matter may be explained by primordial black holes, which are tiny black holes that originated shortly after the Big Bang. Moreover, the notion of black hole thermodynamics has become an intriguing area of study. This paradigm suggests that black holes follow the rules of thermodynamics since they have temperature and entropy. The concept that black holes can release radiation, or Hawking radiation, as a result of quantum phenomena close to the event horizon was first proposed by renowned physicist Stephen Hawking. Intriguing implications about the ultimate fate of black holes and the information paradox itself result from this radiation, which suggests that black holes are not entirely black and may eventually evaporate over astronomical timescales. It also raises important questions about the nature of information in physics. Information cannot be destroyed, which is in contradiction to the idea that matter that goes into a black hole appears to be lost forever. Physicists have been debating this paradox and have come up with a number of theories to explain it, some of which even claim that information could be stored in the radiation that the black hole emits. Black holes are significant scientifically, but they have also captivated the interest of popular culture, showing up in a vast number of movies, books, and works of art. Their depiction frequently tends toward the dramatic and enigmatic, reflecting people's curiosity about the unknown. Black holes cast doubt on our understanding of reality by acting as a potent metaphor for unfathomable forces and the boundaries of human comprehension. Scientists are still investigating the surroundings of black holes, especially the accretion disks that are created when material spirals inward. These disks are among the brightest objects in the cosmos because of their ability to release powerful radiation across the electromagnetic spectrum. Supermassive black holes at the centers of far-off galaxies fuel quasars, which are observed to shed light on the behavior of matter in strong gravitational fields and cosmic evolution. Furthermore, the dynamics of galaxy creation and evolution might involve black holes. Interactions between black holes and the galaxies they inhabit can control how stars originate and affect how matter is distributed throughout the cosmos. Galaxy mergers, which are frequently followed by black hole collisions, have the power to drastically alter cosmic structures and add to the intricate web of the cosmos.